I hope you all had a good lunch. We're going to start off with a more technical talk from Alejandro Russo from Chalmers University and DePella.
Yep.
And he's going to tell us about information flow and the GDPR.
That's right. Thank you. Thanks, everyone. All right, yeah. So in this talk, I'm going to talk about some motivation about the research area that I've been doing, a new motivation I found in a research area that I've been doing for 10, 15 years. And I hope to transmit the enthusiasm to you as well. And then we will go a little bit more technical in that area. And then we will wrap up with some reflections that I have about doing research in PL that perhaps it will help you out in your own research in the future. So what was my research? My research was mainly focused on confinement. What does it mean, confinement? Today we have like a user interacting with computer system. The box is a computer system. And sorry, that system can store data in persistent storage. And it has internet connection because it's 2024, right? So we have internet connection from where we always take resources from. Okay? This is pretty similar. You can almost any system you can map it to this architecture. So the user will provide data. Sometimes it will provide personal data, private data, and it can go to the persistent storage. That's fine. But then does it leak on the internet? That's the personal data that you provide to the computers. Goes to places where you don't know. And that's the main challenge. How do we build systems that confine sensitive data? Well, confine means like I know it remains within the boundaries of the system and it doesn't go to anywhere that I'm not giving authorization to go. All right, so this is the outline of the talk. We will go through motivation, research. These are the more technical parts. And then impact, communities, and general learning. The part that you see on below is especially tuned for PLMW. The rest is more technical conference style of talk. All right, motivation. Today, we are putting a lot of information into computers, a lot of personal information, and that needs to be taken care in a special way. And in Europe, we have what is called GDPR, the General Data Protection Regulation, which dictates how computer systems should handle your personal information, giving you as a user rights on your own, on the information that you generate. Okay, this regulation is from 2018. And how well are we doing following it? So, yeah, so there you can see that there is 2.77 billion euros in fines. Computer systems that do not follow GDPR. GDPR is a monster. I mean, it's really a big regulation. So, yeah. But what I want you to see is like the number of fines and the numbers of amount of money being paid is accumulating quite quickly. Okay? Right. So, how do we deal with this, with GDPR in a way? How we build software in a way that can follow many of the principles of GDPR. The regulation is structured in principles, and computer systems should follow those principles. Okay? GDPR has as well some part which is social and legal. Like, you need to have in your company someone that is called data protection officer. We will not focus on that. We will focus on principles that we can enforce in a technical way. And here you have many of the principles. We will go through them. But these are widely applicable. So these are one of the main principles of GDPR. And the ones that I believe can be automatically enforced. Okay? I have no answer to how to enforce them in an automatic way. But I give you an intuition why I think my research could help into that. Okay? Yeah. And if you look into all the fines, you will see that they violate most of, one, two, or three of these principles. And you will say, well, but you come from Sweden, right? So you care about GDPR because you're European. I don't care about that, right? But then, in China, we have now PIPL, which is similar to some extent to GDPR, inspired by GDPR. We have in Brazil one that is pretty much a copy and paste of GDPR. And then we have the California Consumer Privacy Act, which is also inspired by GDPR. So GDPR is leading the way with these principles of how the future of computer system should handle personal data. Okay? Right, and my insight is the following. That's, I mean, a bit hand-wavy, but GDPR, those principles, can be seen as controlling how information moves in the system, plus doing what is called safeguard data disclosure. Safeguard data disclosure means that when you publish data, you are not putting the privacy of anyone at risk. Okay? So, let's go through the different ones. For example, right to consent or withdraw. Right to consent means like when you collect information, a system collects information that is personal to you, it needs to ask for your consent. You need to agree with that. And at any point, you can withdraw that consent and say, I don't give you more permission to collect my personal data. This is about switching on and off an information flow. Information flow from here to there, and then you cut it. Transparency and auditing is about, you need to show in your system how handle personal data, where the personal data of the users go. And you need to be able to show that. And that's about tracking where data has been sent. No identifiable data disclosure means what I just said before, that when you publish data about a set of users, for example, you should not put the privacy of anyone at risk. Purpose means when you collect data, you can only process it for the purpose that you give consent to. That information cannot be used for anything else, right? Except for the thing that you agree upon. And that means for information flow, it's like it only will go to the part of the system that you give consent to process it. It should not go anywhere else. Data portability means you have the right to ask information about you and get that information in a machine-readable manner. But for doing that, you need to know where your data is. So you need to know where the data that you have right to the system has been propagated, where it has been flowed, because you need to collect it and then give it to the user. Data minimization means you only ask the data, the minimum data that is necessary for the purpose to process the data. And here you can see, from a system perspective, you can see this is my output. If we go back in the processing pipeline, these are the inputs that I need. I need to reason how the outputs are dependent on the inputs. And processing control means at any time you can say that you want to stop the processing of your personal data, and you have the right to do so. Right? So your data is flowing in the system, and at some point you need to cut it. Okay? As you can see, it's all about locating where the data is and how it's flowing within the system. I believe that those principles can be all addressed with the information flow, a research called as information flow control. And safeguard data disclosure with a different technique called differential privacy. Okay? These are my insights about how I believe that this can be solved. It has not been done, has not been explored, but I believe so that there is a lot of potential there. All right. So now let me show you information flow control, which is like reasoning how data moves and enabling data moves in one way with another and restricting that data moves in one way or another. Okay? And for that, we go to my research. Remember, that was my problem, right? So, yeah. One thing that you should be aware of is like enforcing confinement is not about giving access to the data or not. It's not like I need to give access to the private information or not. It's about once I give you access to that data, it shouldn't spread widely. I need to confine it. Okay? It's about how you handle the information. It's not if I give you access or not. And it's known as information flow control or mandatory access control, depending if you come from the PL community or the operating system community. Right? And I have discussion with people in the post community, and one say that the other one is not general, and one, they fight which one's right. I will not get into that. Yeah. So this idea of tracking how information propagates in your programs has been explored by many researchers, and there are even compilers like Chief that you write Java programs and you can reason how data moves within the program. Okay? And making sure that sensitive information doesn't go to unwanted places. We have Paragon, which is from Chalmers. Then we have GSFlow, which is from Chalmers, but it's for JavaScript. Paragon is also for Java, sorry. And Cowl, which is from JavaScript, and the list go on and go on. People have done it for compilers, for interpreters, for operating systems. A different level of abstraction, how to track information, how information moves. In the whole ecosystem that we have here, we have Haskell. That plays a unique role, which is like you can do information flow or tracking how information moves by just providing a library. And you say, well, why is that important? Because for the operating systems, the compilers or the interpreters you see on the screen, you need to modify the compiler. You need to modify the interpreter. You need to modify the operating system. And that's a lot of work, right? In a pure functional language, we can provide it as a library, which is great. But why this works in Haskell and it doesn't work in OCaml, for example? Nothing wrong with OCaml, but why it doesn't work with OCaml? And it's because Haskell has a type system and has decided to have a type system that partition side-effect-free computations from side-effectful ones. Right? So you have side-effect code. Side-effect code is intrinsically confined. You know that the information you put in the input of the function goes to the output and it doesn't go anywhere else. In the side-effectful code, you can do whatever you want, right? So it's like I get an input, my function gets an input, and then that information can go over the network, right? And Haskell has the I/O monad that says, here it's indicating you, it's signaling here there might be some side effects. Be careful, right? That's right. So let's see a concrete example about this. I'm Alice, I'm writing a password manager, and I want to refrain users to pick commonly used password, like 1, 2, 3, 4. Alice is very lazy, doesn't want to write code. So she looks for some code that is provided by Bob, a ninja. Right? He's a ninja programmer. And then what do? Alice will use that code. So when the users provide the passwords, it will go to Bob, to the code that Bob wrote, and go back to Alice and say, yes, it's a commonly used password or it's not a commonly used password. The problem is you don't know if Bob code will make a copy of the password and send it to the server. Right? How can we show that that's not the case? All right, now let's go for some challenge. Bob provides the following type from the common function, which is the function that checks if your password is commonly used or not. This is the type. So I want to see how many of you will use that function. If you are Alice. 1, 2, 3. It's everyone very careful now. Right. This is a pure function. So it's strictly confined. So you know that the password doesn't go anywhere. You can use it. But the problem is you need to hard code the dictionary of commonly used passwords. Okay? It needs to be coded in that function. Now, if common has this type, a string to IO bool, who will use it? Raise your hand. Nobody, right? Why? Because it has the power to do everything. You get a string, and then it can do whatever it wants. Right. So now I tell you, well, then the problem is you are doing a lot of things with the IO monad. You have the power to do many things. I said, well, actually, the code has now the type safe IO that has one side effect, which is fetching dictionary updates. That's it. It cannot do anything else. Will you use that function? Do you use it? A couple of things. Say no. All right. The answer is even in the request of the dictionary update, you can encode the password information. All right? So no. All right. So then what do we do then? Right? And what I'm going to show you here is a functional pair I wrote in 2015. where, I found it the simplest way to present information flow control and how to solve the problem, the dilemma of Alice and Bob in the password manager. So we are going to make Bob sure that use some security types, and by Bob using those types, I can be sure that the information is not being leaked, while the Bob code can still fetch dictionary updates. Okay? We're going to provide a family of monads. Ideally, it's like you start with a super liberal monad. As soon as you read a secret, now the monad only will perform side effects which do not leak information. Okay? Right. So, and we, I'm not going to show you all of that, but in a functional pair, you can see how to deal with very advanced. These are, from the information flow perspective, these are very advanced features. We will do everything in 200 lines of code, and we will use Haskell 98. Probably nobody was, many of you were not born by then. And we will use two type classes. Two extensions, multi-parameter type classes, and save Haskell. And then we go to the save Haskell part in a bit. All right. So the first thing, this is the introduction to information flow control in maybe 10 minutes. It's like we start choosing a security level. A security level, it represents how sensitive information is. And I'm going to accommodate all the security levels in a lattice. It's not necessary, but it's convenient. We put it in a lattice. And the important thing is like information can flow from data with a security level from the lower to the highest part of the lattice. All right? So I'm going to give you an example. This is the thing you need to remember. If I have two labels, information with label L can flow into entities of label L prime if L is below in the lattice than L prime. Okay? So, for this talk, we are going to choose a 2-point lattice. I have only 2 points in the lattice. One is L of low for public and H or high for secret. And low flows into high, but not the other way around. Okay? So the lattice is telling us the policy about how information is allowed to flow. So, okay, how do we encode this in Haskell? Every point in the lattice, we make it an abstract data type. And how do we encode the order relationship? We have a type class that has instances, all the allowed ones, and there is only one missing, which is going from high to low. Okay, so the compiler knows about the security levels and what information can go from L to H. All right, now that we have security levels, how do we put labels in data? Right? We have another abstract data type called label, LA, that says A has label L. Example, a credit card is a secret integer. We'll have type label HInt. A weather report is a public string, which has a label L attached to it. Okay? Great. We can classify the sensitivity information. We can attach it to data. How do we build computations now that make sure that we don't leak sensitive information? And for that, we have an extra abstract data type called Mac, LA. And essentially, it's a wrapper of I/O. So Mac LA underneath will have I/O actions that are guaranteed to not leak information. But we will go in a second how we will build that. And the way that you think about this is like Mac LA is a side-effectful computation that handles all information at level L and produces a result A of level L as well. Example. We have public is a Mac L string. It means like it's a computation that does things with public data, only with public data, and it produces a public integer. Secret, handle all sensitive information, and produce a secret string. Okay. Now we have a family of monads. Monads are indexed by the security level, so we have Mac L, Mac H. Okay. One dealing with public data, one dealing with secret data. And then, as you can see, it's just a wrapper on I/O. You have the run function that just gives you the I/O actions underneath. That run function is not going to be used by Bob, the developer. It's going to be used by Alice. Right? Bob, the developer, we will see in a second, will only use the interface for Mac. Right. Mac comes from mandatory access control. And how can we build secure computation for that? And for that, I'm going to take some principle from operating system research from 73, where not even I was born. So by transitivity, none of you were born. So Mac LH, this principle says the following. In the abstract sense, a computation can read and write data. Right? If I read data, that data has some label, LRead. It's okay for that data to flow into the computation, which has label L, if LRead is less than, equal than L. Okay? This is called the no read up principle. A computation is secure if you are at a certain level, you can only read things that are less sensitive than you. Now, if you write into a sink, that sink is also labeled with LWrite. And now the information needs to move from the computation into the sink. Right? So now I need to check that L is less equal than LWrite. This is known as the no write down. A computation is secure if I'm at a certain level and I only write above me, never below. If you are a secret computation, you cannot write into a public file because you might be leaking sensitive information. All right. Now, let me give you an example of a very simple source and sink of information, which are Haskell expressions. Right? Label LA, you can think that as a source or sink of information, where the A is the information is expression of type A. We will have two functions, label and unlabel. The first one, what it does, you take an expression of type A and you create a label value. You put it inside a label data type. Since we are creating is like writing. It's like, and I need to allocate an empty piece of memory and then write something into it. Right? So therefore, I have a MacL computation creating something of type label L create A. I need to write, if I'm MacL, I need to write things above me. That's the no write down policy as a type constraint. The unlabel is the reading. You have a label source with LRead, and you will expose it to the computation. Therefore, to flow into the computation, it needs to be the case that LRead flows into L. That's the no write up policy. So these two principles of operating system are captured as type constraints. And this is the most simple example, but if you tweak A here, you specialize it a little bit, you can have references and M bars. You can have different abstractions which are aware about information flow control. You can have a Mac computation that does read and write references in a secure way. All right. So let's go back to the example, Bob. Now I said to Bob, this is the type I want for your for the routine to check commonly used password. I want you to take a secret string, and now as a result, I will get a MacL computation. This is the MacL computation that deals with public information. This is the one that fetches dictionary updates. And as a result of that, after that, I get a MacH computation, which checks if the password is inside the thing that I have just fetched. Alice, what it does, asks the user, what is your password? And I will wrap it in a label H string type within a MacL computation. And now you can see the, do I have this? Yeah, no. You see the label password, now it's given to the piece of code of Bob. And I know that now it's confined. Okay? All right. You run it, you get the MacH, and you run it again. All right, so I give you a super brief version about the security libraries of information flow control, but there are a bunch of different versions of it. I show you MAC, which is a static enforced with using types, but then you have dynamic ones, LIO, or a mixture of these two. So there's a bunch of literature if you're really interested in this area. Going back to GDPR, now that you know information flow control, right? Now imagine that instead of having security levels like L and H, very simple ones, now you have a label that says who this information belongs to. Okay? And now we can track, you know, if I combine information from Ale and Leonidas, it gets combined. Now I say this information belongs to both Ale and Leonidas. If I want to do something with that, I need to ask the consent of Leonidas and Alejandro. Okay? So my idea is to create computations. This kind of computational unit, you can see here, it has three parts. You live inside the computation. That's the area A, where we will use information flow control to keep track who owns which information. Then when you go to area B, which is like you want to store it, then based on the label who this information belongs to, you will choose certain cryptographic keys to write it in an external store. And then when you want to disclose information, the area C, you will use these data disclosure techniques like differential privacy. So this is a project that I'm going to carry out in the next 4 or 5 years, and this is kind of the concept that I'm playing with. And I have a little bit of something to show you here, which is like Haskell last year. We published a paper that started kind of making a reality this kind of model I'm showing you. All right. Right. So now this was the most technical part. So now I will try to. This is PLMW. I'll kind of go through some of my research, the impact of what I mean by impact in my research, communities, and general learning. So hopefully, if you decide to jump in this area or in the area that you're working on, maybe what I'm going to tell you might resonate or might help you out in the future. All right. So what do I mean by impact? When you do research, your impact is like, you know, it can go make the world a better place, solving hard problems, right? But that's very cheesy. Usually what it means is like, I'm in my bubble, let me alone, right, to do with the things that I like. But at some point, you need to go out from your bubble. And how do you get out? You start with what I call, these are my own invention, so it's not brilliant. It's just like something I came up with. But, you know, level 0, publication and citations. When you do your PhD, the way to have some impact is publication and citations. That's the way to you start getting out of your bubble. Then the next level, every level is exponentially hard to achieve, right? So you know, it's not linear. Level 1 is like your research is used by others, right? And I found that writing code and making code available is a very convenient way for others to take on my research. And the library I show you, for example, I took a snapshot. It was like download 2,700 times by December, right? It's some modest impact, I would say. Okay, in the Haskell community, I don't know, what is the most used package in Haskell? And then, so I guess like this kind of issue during your studies, you can address it, or you can start planning addressing it. And then level 2 is like adoption of your ideas in production. This is like taking your idea into the market. And that's very hard. So I created a company 3 years ago to try to take some of my PL research into industry, right? And after 3 years, we don't have a customer yet, hopefully this year. So then you understand how hard it is. Right. Cool. And then you can make the world a better place, right? So this is kind of the stair of impact. All right. So now, one thing I want to encourage you to do is to publish across different research community. So I consider myself like in the middle of these things. At some point, I was confused. I was like, I'm a security guy, then I was a functional programmer, operating system by chance, and, But then I understood that I'm non-binary, so like I'm not identified with any of, of three. So like, and every community. So then we in PL, we have the unique chance to publish in different communities. It doesn't happen with many areas, research areas. So take that advantage. But be aware that each community has different, they focus on different things. What I'm saying now is not sufficient to publish there, but it's very necessary, okay? For example, in functional programming, language design is very important, right? Then in security proofs are very important. In operating system, evaluation is very important. And you say, well, Alejandro, why are you so sure about these kind of things? Well, I went into the source of all truths, which is the rejection reviews of your papers, right? So, language design. We got this for one PL conference. The proof about the language described in section 2 just don't say much about the real world language. So the language design, the language was unsexy, was not real. Soundness. In the end, they obtain essentially the same semantic proof as in 6. They're just blowing smoke and not a contribution. All right? They really went and looked into the proof. Okay? Evaluation. The bulk of the material is fairly abstract and esoteric. It relates almost no experience in actually using the language to build substantial or realistic applications. Okay? So, yeah. So then you understand when you choose a community, try to see what is the main focus that they have to understand how do you get your PL research through them. All right. So now some general learnings that it might help you out in your career. So on the first one, is, recently because of the company, I've been doing some business training, right? And at some point we were reading about the strategy, right? So we faculties at the university, we talk about what is the strategy of the department in the next 5 years, 10 years, or what is the vision of the whole university in 5, 10 years, and things like that. And companies do the same thing. And this is a business study, what it shows through many years what is the impact of a strategy in the success of a company. And you have here, this is like something that is happening in your industry that gives you success. This is the strategy. But then look at the color on the most right hand side. It says other factors. Things that are not part of the strategy. You should have a strategy, yes, but it's not the only thing. That's my message. When I read this, I said, this is bollocks. I mean, doesn't make sense. And then I reflect on my career since I become a professor. I had a strategy. I go to Chalmers to study. In 2004, I got rejected. So I was not good enough to get into Chalmers. 2005, I met Andrei Sabelfeld, who was my advisor during my PhD studies, that he was in an event. I met him, and he was looking for a PhD student and offered me a position on the spot. But the reason for that he offered me the position is that because he hired a person to do the PhD, and 2 weeks before starting, that person resigned. So I got in. Right. My strategy, I should become a faculty at Chalmers. It's a great place, great PL, right? 2010, there was an opening for assistant professorship. I decided not to apply because I was having this issue, I'm more a security guy than a functional programmer. And then the day before the deadline, I came out of the room and I came across Koen Klassen, who is a functional programmer. And he told me, are you applying, Alejandro? I said, no. It's like, I'm not a functional. No, you are, blah, blah. Convinced me the whole night writing the proposal. I sent it in. I didn't win. There were four candidates in the final. The first one was Dimitri Vitibinois, who was one of my co-authors, great guy. The second was myself. Dimitri decided, no, I'm not going to Chalmers. Then I got the position. Huh? So, going back, it's not that bollocks. So, my strategy now is to have a strategy, but also be exposure to luck. What does it mean to be exposure to luck? Try to talk to as many people as you can. Try to network in conferences as much as you can, because you never know where the next luck will come. Where the luck is going to come from. Okay? Right. So, and the second learning, for me, is like, as a PhD student, you need to be ready for failure. You need to be ready for failure because, you will fail. As I show you all my reviews. And for example, I got in 2016, there was a very competitive grant in Sweden for, research leaders across all disciplines. There were 225 applications, and I was number 22nd, and they only granted 20. Huh? So, I was very down by then. Then recently, about 2 years ago, I was in the ERC Consolidator grant. This is one of the most prestigious grants in Europe. There were like 2,600 proposals, only 300 in the interview phase. I was in the interview phase, and then didn't get it. So, what I do when I have this kind of situation, or what are the things that since 2022 I've been doing when I have bad situations? I'm originally from Argentina. What is the most famous sport in Argentina? Football, that's right. So now I took inspiration about this guy, right? Which you might know, Messi. He lost 4 finals. 1 World Cup and 3 American Cup. And he's the most talented guy in football in the whole history. Yeah. All right. I'm biased. But the guy keep pushing. And finally, he made it in 2022. Okay? So the message is like, if the guy has the most talent in the world and keep trying, you can also keep trying. Okay? So, I have show you, to wrap up, I have show you, how I believe data privacy regulations can be tracked or addressed from a foundational way using information flow control. I have shown you information flow control from the point of view of a security library in Haskell, and I show you the core principles of the research area. And as I said before, PL has a tremendous opportunity to make impact across communities. So take advantage of that, or keep that in mind when you do your studies. And hopefully, when you finish and you achieve great success, we will feel like raising your academic World Cup. Thank you very much.
All right, we have a little more than 5 minutes for questions, if people have any.
Hi, thanks for the talk. I was wondering whether, in your type system, you could provide like safety against like timing attacks and sort of other side channels.
Right. Timing is no. The short answer is no, right? And we could be yes, but you need to be very, very conservative, right? So timing is very hard to deal with. Yeah. So these simple kind of libraries are not well prepared for side channels like timing, right? We will be interested to see if you can do something with that. Yeah.
Hi, I have a question about your Max library, and you showing the directions of like data flow. I was thinking about computations which like lose data. So like, for example, if you're taking a hash of a password, have you got some way of like encoding into the library that the data is now safe to become public in a type safe way?
Yeah, what you can do is like when you define what is called the non-proper morphisms of the MAC monad, you can say, well, there is one that say hash, It goes from label H string to label L string, right? But then you give it as a part of the trusting computing base. It's something that you trust that that type signature is correct.
And you have to verify that separately.
That's right. That's right.
Thank you. Very interesting talk. I had two questions, one of which you might have already covered and I didn't notice was, in the Haskell examples, presumably you have to disable things like unsafe before my own.
Thanks a lot. Yeah, I forgot about that. Yeah. Now, let me ask you this. Yeah. Sorry, I didn't deliver on my promise that I will explain you about Safe Haskell. Safe Haskell, Haskell has extensions, which in the name of performance, you really need them. They break type safety and module encapsulation. Safe Haskell is an extension that disables those extensions that break type safety and module encapsulation. So then you can have guarantees that you can trust your types, essentially. Yeah.
And then the other question I had was actually more to do with when you mentioned some tools that work with JavaScript. I'm aware that in JavaScript you have quite pervasively things that essentially amount to some form of metaprogramming, in that I can interpret arbitrary strings as code and various things. When these tools are written for JavaScript, do they essentially somehow just disable those features, or do they do something clever to track this information?
So, I can tell you what I've been working. When we work on information flow and JavaScript, it was a cowl system. We didn't want to mess with the JavaScript semantics because of all these, exotic features, right? So what we did instead is we look. The browser is already provide isolation compartments, like a browsing context or empty JavaScript context. And we kind of put a boundary around that, and then we control what goes out, goes in, right? It's more coarse-grained, but that was the best way we found to I don't care what you do with JavaScript, these fancy features, I just control what gets in and gets out. As long as something secret gets in, everything gets tainted, right? And then the communication might get restricted to the outside world, yeah.
Thanks for the talk. You mentioned that you'd produced a library that had quite a lot of success. Obviously, there's lots of features, lots of prerequisites for this. So it has to be well designed, have a nice API. Maybe you publish a paper that provides the theory. But you can do all of these things and it not take off. You could have a great system that's brilliant user interface, solid foundation that's been published, but no one uses it. So is there anything you did outside of these design factors that encouraged it to be picked up by the applied community, or was that another luck factor? Right.
So I would say that I don't know if 2000 something will take off in the information flow community. I don't know, but maybe. But I would say no. We didn't do anything. We just publish the paper, write in the code. We focus a lot on simplicity. I think simplicity is key, right? So sometimes you need to do some. If you look, I remember my first paper. They were super complicated because as a PhD student, I want to throw all this. I want to demonstrate that I can handle a lot of complicated stuff. But the more I advance in my career, the more maybe my mind is reducing capacity. But the more simple I become, and I think that's kind of one thing that we did consciously with LIO and Mac and the work in JavaScript, cow, to be as simple as possible, and that's got some traction. Yeah.
Okay, thanks.
All right, I think we're going to have to cut it off there. Let's thank Ale again.
Thank you very much.